Swayam Prabha. Digital India. Educated India.
Good day everyone and welcome to these lectures on physico-chemical processes for wastewater treatment. So, in the previous lecture we started studying advanced oxidation processes which are referred to as AOPs, and in the previous lecture we studied that during AOPs the key thing is the production of the various reactive oxygen species such as hydroxyl radical during the treatment process itself. Now, these reactive oxidation species further combined with the organic compounds which are present in the water, and they mineralize these compounds into CO2 and H2O. So, these were the major techniques or the steps which are there in the advanced oxidation processes. Now, in addition we learned that depending upon that how these reactive oxygen species are generated, there are different types of AOPs like Fenton oxidation processes, ozone treatment, photocatalysis, electrochemical treatment, ultrasound, etc. Now, these advanced oxidation processes work differently and they have different mechanism how they produce reactive oxygen species. There are different combination of different processes AOPs possible also. So, we are going to start with few of these AOPs in the today's lecture. So, we will start with the Fenton processes which are there. So, Fenton reaction was first reported by H. J. Fenton in 1894, and actually this Fenton reaction has been used further for treatment of water. So, in this case in the Fenton reaction or Fenton processes, we have iron which is used as a catalyst. Now, this iron under acidic condition will remain in the form of Fe2 plus, which is the desirability. Now, if we have some hydrogen peroxide is added beforehand, then it initiates a process where a lot of reactive intermediates such as hydroxyl radicals are produced, and they further unselectively oxidize most of the organic compounds present in the water itself. So, several other radicals etc. and reactive intermediates etc. may also get formed because of the action of Fe2 plus H2O2 under acidic condition with the different organic compounds which may be the present in the water. So, the Fenton reagents are Fe2 plus with H2O2, Fe3 plus with H2O2 or Fe2 plus with some ligand and H2O2. So, this is called as Fenton reagent, and this is used for the treatment of the water. Now, there are different reactions which are involved in the Fenton processes. So, these reactions are given here. So, we can see that Fe2 plus may combine with hydrogen peroxide to form Fe3 plus and the OH radical and OH minus ion. So, this is possibility. So, Fe2 plus with H2O2 in combination may form Fe3 plus and some radicals are getting generated. So, this is there. Now, this radical also may combine with the hydrogen peroxide itself and give back the Fe3 plus ion and some other types of radical during this process. Now, Fe2 plus itself may combine with the radical produced to form Fe3 plus. Now, this Fe3 plus can combine with the peroxy radical to form Fe2 plus ion or O2. So, there are different, and OH radicals may combine to form H2O2. So, some of these reactions are undesirable. In particular, this reaction we do not want to happen, because we want hydroxyl radical to present in the water. So, this is undesirable reaction and we want to avoid this possibility during the treatment. The organic compounds will combine with these radicals and produce degraded product during the treatment. So, this is the basic mechanism by which this Fenton process work. Now, the classical Fenton process takes place in a homogeneous system. The processes that involve reactions between iron in an insoluble form, either in unsupported form such as mineral particle or etc., or they may be supported on some substrate which could be particle or a membrane etc. So, it is possible that iron may be supported on a substrate. So, this is also possible. Along with the iron we have H2O2, and if we are using this technique, so under that technique it is called as heterogeneous Fenton processes. The iron can be initially in the form of Fe2 plus or Fe3 plus, because the reaction of Fe3 plus with H2O2 will still generate Fe2 plus. So, this is iron may be in any of these form. Okay, so, this is there. Now, going further, the effectiveness of the Fenton process, it can be improved further if we are using some external non-chemical energy sources. So, we require some, if we are providing some energy sources, it will increase the possibility of formation of different types of radicals. So, these external non-chemical energy sources may be ultraviolet light, may be electric current, may be ultrasound etc. So, this is all, any of them is possible, but whether to use them or not use them, that will depend upon the wastewater to be treated, some laboratory studies to be carried out beforehand, otherwise the energy consumption may increase. So, this is possible. Now, these, if we are combining the Fenton processes with these are called as extended Fenton processes. Then there is another term which is called as Fenton like processes. So, which are similar to Fenton, but where iron is not being used. So, this is there. So, the term Fenton like process is sometimes referred to any process that has similar feature to the Fenton process, but is not the classical process, and will include like heterogeneous processes, processes that use Fe initially in the Fe3 plus form. So, classically it was Fe2 plus form. Similarly, we can use other types of similar like Mg2 plus etc. So, other types of catalyst having with some other metals elements etc. can also be used. So, these are called as Fenton like processes. Now, Fenton type processes involve iron in any form as a catalyst and use H2O2 as an oxidant. It is, so this H2O2 and these are added directly as a reagent, or they may be formed in situ as well, such as by electrochemical reaction or by the photolysis of Fe3 plus complexes. So, this is possible. So, they may be added directly, they may be generated in situ also. The term Fenton like processes should be reserved for all the processes that have similar chemistry to the Fenton process. So, this is there, but they involve metallic catalysts other than the iron, or also oxidants that are not H2O2. So, this is there. So, these are called Fenton like processes as discussed. Now, there are different types of Fenton processes. So, already we have discussed, we have homogeneous Fenton process, we have heterogeneous Fenton processes. Now, in the homogeneous Fenton processes, all the reactions take place in the aqueous phase itself, whereas in the heterogeneous Fenton processes, the reactions take place in both the aqueous phase and the solid phase both. So, this is the difference between homogeneous and heterogeneous Fenton processes. Iron catalyst, that is in the solid phase, and this can be supported on a substrate such as zeolite, polymeric membrane, etc., or it may be existing in the unsupported form. So, depending upon that, it may be homogeneous phase, heterogeneous phase, etc. Now, homogeneous Fenton processes, they make use of iron in the aqueous phase or iron in the iron 2 or iron 3 in the aqueous phase as a catalyst. When these processes occur in the absence of suitable wavelength light to cause photo reduction of Fe3 plus complexes, they are called as dark Fenton processes or thermal Fenton processes. So, this is another classification of Fenton processes. Now, homogeneous Fenton region in the aqueous system, we have Fe2 plus with H2O2, Fe3 plus with H2O2 or Fe2 plus with ligand in the aqueous phase with H2O2. So, this is there. In the heterogeneous Fenton process, they use iron in Fe2 plus or 3 plus form in the solid form as a catalyst. The use of iron, that is initially in the solid form, that reduces the amount of sludge that is formed, and iron can be present in the unsupported form or it can be supported on any of the polymer, any of the zeolite or membrane matrix as well. Now, there is another thing which is called as extended Fenton processes. So, several types of non-external non-chemical energy sources have been used in conjunction with the Fenton regions. So, any of these energy sources, if they are used along with the Fenton processes, they are referred to as extended Fenton processes. These energy sources may include ultraviolet, microwave, gamma radiation, ultrasonic radiation, electrical energy, etc. So, these are called as extended Fenton process. Now, within extended Fenton processes, the types of extended Fenton processes in which external energy is used are like UV visual light. So, it is called as UV Fenton or photo Fenton. Electrical energy, we have call it electro Fenton. Then ultrasound, it is called as sono Fenton. So, combination of these extended Fenton processes is also possible and they are referred to as hybrid Fenton processes, and so these are like sono, photo, electro. So, all three are combined, sono, photo, Fenton process. So, two more possibilities, photo, electro Fenton processes, this is another possibility. So, in this case we are using Fe2 plus with H2O2 in the aqueous form or in the solid form also we can use. So, this is there, we are using ultraviolet here. So, you can see here. Then we have heterogeneous photo Fenton processes. So, heterogeneous Fenton process can be used carried out using iron catalyst in the supported form only, as unsupported solid iron catalyst will block the light path. So, this is possibility. So, in this case it is called heterogeneous photo Fenton process. The supported heterogeneous catalyst that can be used in the presence of light include like absorbed iron third or iron ions or iron third oxides on different types of supports including zeolites and membranes. Then we have electro-Fenton processes. So, two types of Fenton process that involve in situ electrochemical production of reagents. So, that may be cathodic Fenton processes and anodic Fenton processes. So, iron is added in this case as Fe2 plus or Fe3 plus salt, and in this case the sacrificial anode will generate the iron in the zero valency. So, it has no valency, but it will get converted into Fe2 plus Fe3 plus for further uses. So, this cathodic Fenton and anodic Fenton both are possible. Then there is a sono-Fenton process also, in which H2O2 is produced during standard sono-chemical treatment process. So, hence the addition of Fe2 plus can further enhance this process by converting this H2O2 to OH radical. So, this is there, and thereby it accelerates the contaminant destruction, and we are able to mineralize the contaminant very quickly. The main advantage of using the sono-Fenton process is that the cost of sono-Fenton processes may be much lower due to shorter treatment time which is there with respect to sono-Fenton process. So, this is a possibility, and that is how the sono-Fenton process work. Then we have discussed Fenton like processes. So, this is another key thing. So, weighed a large number of trace metals can also react with H2O2 to yield very highly reactive oxidants. So, this is possible. They may be OH radical, they may not be OH radical, but they can react, and it is possible to generate hypochlorite peroxy disulfate. So, this is another type of reactive oxygen species. Then we have hydroperoxides which may be formed in addition to or in place of H2O2, and so we can use many trace metals. These may be copper, cobalt, manganese, titania, etc. The reactive intermediate of these systems may include like this Cu1 H2O2 system is maybe a this copper third species. Okay. It may be possible to produce OH radical under certain condition. It is also possible that other types of radicals are getting generated. Now, all these radicals, they will combine together, they will react with the organic compounds present in the water, and thus they will mineralize these organic compounds into CO2, H2O, etc. So, these are called Fenton like processes. So, there are different possibilities of Fenton processes. The key thing is that in the Fenton processes we have H2O2 which is used along with the iron catalyst. So, that iron is either in the Fe2 plus form and Fe3 plus form. Fenton system works more very well for water which is having low pH around 4 or less. So, these are the key observations that have been reported in the literature with respect to treatment of water by Fenton like processes. So, this is there. Now, we will go further and study another AOP technique which is called as ozone treatment process. So, in the ozone treatment process, ozone is used in drinking water applications to meet multiple objectives. So, ozone can be used various ways. So, it can be used for disinfection, for minimizing taste and odor. So, if any water is containing odor or any of the pathogens are also present, so it will be able to destruct all those things which are present in the water. So, it will reduce the formation of disinfectant byproducts, thus oxidizing. In addition, it will oxidize the organic compounds present in the water. So, ozone has the ability to produce to inactivate the pathogens and to oxidize most of the organic contaminants present in the water. So, ozone can be used differently. Now, for doing this we need to produce the ozone. Now, the ozone molecule is composed of 3 atoms you can see here. So, it can resonate in different forms, these 2 forms depending upon the pH and other conditions. So, it may be there. So, this is the ozone molecule. The electron density and the distribution across the ozone molecule causes it to be highly unstable. So, it will always be highly unstable. It may deteriorate very quickly and form oxygen. So, this is there, but before it happens we have to use the oxygen molecule, ozone molecule for destructing the contaminants present in the water. Now, decomposition of ozone, how it happens in the water? The reaction occurs via transfer of an oxygen atom to form HO2 minus and molecular oxygen. So, this is how the ozone will decrease very quickly. The reaction would then yield OH radical via series of additional reactions. So, it is possible that ozone will form different types of OH radical or peroxy radical etc. So, this is possible during ozone treatment. We can see here different series of reactions are happening before the OH radical is getting formed. In natural waters including surface water and also in the usual wastewater, the decomposition of ozone occurs via reaction with reactive groups within the dissolved organic matter. So, many dissolved organic matter may be present in the these natural water. So, ozone will combine with them and form degrade. So, which is undesirable. We want ozone to react with the organic compounds and convert them or mineralize them. Now, ozone based AOPs, there are different ozone based AOPs which are used for wastewater treatment. The 2 common methods include hydrogen with hydrogen peroxide and with photolysis. So, this is there. So, if with hydrogen peroxide it will called as O3H2O2. So, this is with, we can see here the peroxide is there and ozone is there. Similarly, ozone in combination with UV is also possible. Now, this the first process is called as peroxone process as well. So, we are going to study this process in detail here. So, this process describes the generation of OH radical from the reaction of ozone with hydrogen peroxide. The reaction of O3 with hydrogen peroxide is slower, but that can be but with its anion H2O2 minus ion, it is several orders of magnitude faster. So, if it reacts with H2O2 directly, it will be slower, but it can react very quickly with this anion of hydrogen peroxide. Due to high pK value of H2O2 which is around 11.8, the reaction is fast only at elevated pH. So, if any wastewater is there which is having pH around 10 or 12, then under those conditions the reaction of ozone with H2O2 will be very quick. So, this is there. A summarized overall reaction of various elementary steps which are there during ozone reaction with H2O2 are given here. So, hydrogen peroxide may form this anion. This anion further reacts with ozone to form peroxy radical. This peroxy radical may give another oxygen radical. Okay. Oxygen radical may combine with ozone to form other types of oxygen reactive oxygen species which further react to form hydroxyl radical. So, the steps are number of elementary steps are involved before hydroxy radical gets formed from the ozone and hydrogen peroxide. Now, this is there. In conventional ozonation, typically 2 kinetic regimes of ozone decay are observed. So, if we have utilizing the ozone, so how the ozone decreases? So, this is the representation of ozone decay in ozonation as well as peroxone process is given here. So, in the ozonation there will be one step, then there will be a second step, whereas in the peroxone process there will be a single step degradation only. So, in the usual ozonation, conventional ozonation, the first rapid step is there, then there is a slower second step. The kinetics of ozone decay in the peroxone process is constant over the whole range. We can see here it is overall constant. So, it displays two phases in the ozone only, whereas it shows only one phase in the peroxone process. So, this is there. Now, photocatalytic ozonation is also possible. We are not using H2O2. So, we are not using any hydrogen peroxide. Here the treatment is being done without hydrogen peroxide, but in the presence of ultraviolet light. The molar absorption coefficient of ozone is much higher in the relative UV wavelength range. So, like if the lambda is 253.7, which is one of the key wavelength for destruction of pathogens. So, under that condition the molar absorption coefficient of ozone is very high, okay, as compared to that of H2O2 itself. So, the photolysis of ozone is much more efficient than photolysis of H2O2 itself. So, this is the reason that O3 in combination is UV can be highly beneficial as well as highly efficient process for wastewater treatment. Now, O3 has an absorption coefficient, absorption maxima at 260 nanometer, and where the lambda here for usual pathogen destruction is 253.7. So, the difference is not much. A low pressure mercury lamp, okay, is suitable for photolysis of O3, as it will emit this 253.7 nanometer wavelength UV light. So, this low pressure mercury lamp along with ozone can be used for treatment of water. Light sources emitting light at wavelength greater than 300 nanometer are not applicable for this ozone UV process. So, we have to use this mercury lamp, low pressure mercury lamp, etc. So, we can see the UV spectrum of ozone in water with different phases like UVA, UVB, UVC ranges. So, this is there, and in the inset the full spectrum is given from 190 to 800 meters. So, we can see here that the low pressure HG lamp emits UV in this wavelength, whereas the maximum for ozone spectrum is at 260. So, that means in the UVC range, near to this range we have the highest efficiency, and there is a good possibility that we can combine together. So, this way ozone along with UV is a good combination for further use in the wastewater treatment and for degradation of pollutant in the wastewater. The photolysis of ozone yields oxygen atoms and molecular oxygen in their ground or excited states in the solvent case. So, this is possible. Okay. Now, the species are like here O1D, oxygen atom in its excited state, then O3P, this is also possible, this is oxygen atom in its ground state. Then we have singlet oxygen which is produced here, then as well as in its ground state also. So, this is also possible that these may be getting produced. Now, these species are involved both in recombination reactions within the cage. So, this is also possible that, but we always wish that recombination within themselves it should not occur. They should react with the contaminants first, and they should be able to degrade these contaminants into CO2 H2O. So, this is more desirable. if escaped from the solvent cage in the reaction, the water molecules or other compounds present in the solution. So, this is there. So, we want this reaction to happen. So, these species should combine with the contaminants, which is desirable. Now, out of this, O1D is highly energetic and more electrophilic and more prone to undergo bond formation, addition reactions than the other types of compounds which are getting formed. So, this particular compound is more active in degrading the compounds. So, this can thermalize or break into 2H radicals. So, and these 2H radicals can further react with the contaminant. So, this is there. So, thus the overall limiting the this particular reaction is the diffusion into the bulk solution. So, how they come out of the cage and go into the bulk solution and react with the contaminants present there. So, if we can enhance this diffusion reaction, the overall treatment time will further goes down. So, this is there. So, the most of the generated O1D they yield H2O2 and which can further be used for generating radical etc. So, this is how the ozone treatment processes work. Ozone treatment processes have become very common and in fact, household type of simple ozone generators have been developed recently and they are used for cleaning of the surfaces of vegetables, fruits etc. also. So, they are low intensity ozone generator. The key aspect with respect to using these ozone generators is that they should not be combining with our body or our body system, because then they will be degrading some of the cells etc. in our body. So, their ozone as such at the ground level is detrimental to human health as well as to the plants, but if it is used in the water for contaminant removal without any ozone coming out of the water, then it is good. Now, if some amount of ozone comes out of the water, but it reacts very quickly or it degrades into oxygen species, then there is no issue. So, we have to be little bit careful when we using ozone. So, we have to see that none of the ozone is coming out of the water and it should get converted into oxygen before being released into the atmosphere. So, this is the key aspect, but overall the Fenton processes along with the ozone treatment processes are becoming very common and lot of research and other design aspects of studies are going on towards using these processes for common wastewater treatment techniques as well. So, one of the techniques which is well reported in the literature is it is called catalytic wet peroxide oxidation. So, in this technique what we do is that we use peroxides along with some catalysts for wastewater treatment. So, the CWPO, which is the abbreviation of this technology. So, this process uses water insoluble solid catalyst. So, we can use some catalysts which can form radicals, and using this water insoluble solid catalyst we can generate lot of radicals in the reactive oxygen species in the wastewater, and this technique actually overcomes all the shortcomings of homogeneous Fenton reaction. Similarly, in the heterogeneous Fenton reaction also, only we can use the Fenton technique up to a certain pH, and generally it is applicable in the acidic range. So, this technique can be used at the other pH conditions also. So, this is there. So, it may be used for treatment of water at other pH, wide range of pH. So, this is possible without leaching of iron or any other metal or producing sludge. So, all the three aspects we are benefiting by using this technique, and also it may be having superior oxidation efficiency. So, this is possible depending upon the type of wastewater we are treating, the type of catalyst that we are using. So, this is there. In the wet peroxidation method, we always use H2O2. So, we always use hydrogen peroxide, and actually it is converted into some radicals using some catalyst surface. So, here example is given for Fe2 plus Fe3 plus, but it can be used for other types of catalyst also. So, this is possible. So, we can see here this particular reaction will happen when Fe3 plus is getting converted into Fe2 plus, but if Fe2 plus is getting converted into Fe3 plus, still the H2O2 will generate hydroxyl radical and they will oxidize any organic pollutant present in the water and convert them into oxidized products which are like CO2, H2O or other mineral acids. So, this is the what is desirable using catalytic wet peroxidation technique. Now, some water insoluble catalysts that are used for treatment, they should have following desirable characteristics. They should be as efficient as iron salt in the homogeneous Fenton process, but stable with minimum metal leaching. So, if we are using any catalyst, it should not leach into the water, or if it is leaching, it should be within the desirable metal concentration limit as set by Minas, one thing, and it should be usable for very long duration. So, this is there. The catalyst should have large surface area and a large number of catalytic sites for performing these steps which are shown in the previous slide. They should be active in the wide range of pH and at lower temperatures. So, many times the catalyst may work, but we may require the temperature to increase. So, it is desirable that these catalysts should work at lower temperature. The main reason for using catalyst in CWPO is to accelerate the rate of hydroxyl radical generation and thus increase the rate of pollutant degradation. So, this is there using this technique. Now, the Fe2 plus ion or Fe3 plus ion or any other catalyst may leach into the solution under acidic condition, and that will contribute to the oxidation via homogeneous Fenton process. This is of course an unfavorable side reaction in heterogeneous CWPO, which reduces the activity of the catalyst, because with time the catalyst amount will decrease, the activity will also reduce because the leaching is happening, and in addition the metal is going into the water, which may not be desirable. So, majority of the catalysts synthesized for Fenton or CW processes are based upon iron salts, but any other salt can also be used. So, other salts include like copper, manganese, cobalt, etc. They also have been reported for CWPO process. Now, CWPO performance, how it works? So, it is a temperature dependent one thing, and the degradation rate of organic pollutant generally we know it increases by increasing the temperature. So, the CWPO process normally needs a slightly higher concentration of H2O2 and a slightly higher temperature than the ambient temperature to show their best performance. So, what we do is that we generally try to find out the amount of H2O2 required, and that H2O2 requirement is done with respect to stoichiometric H2O2 requirement. So, we can always perform some calculation beforehand, like suppose the compound is CXHYOZ or any other sulfur, nitrogen, etc. is there. So, we can perform some calculation that what is the requirement for converting this into CO2, H2O, etc. So, we know from here the whatever is the value, that what is the stoichiometric H2O2 requirement. So, we test that with respect to stoichiometric H2O2 requirement, what is the actual H2O2 requirement. So, that can, this optimization can be done by performing the lab scale studies. So, and after that we can use the usual catalytic reactor design approach for using the catalyst for wastewater treatment. The utilization of the CWPO process depends upon the development of solid catalyst with high efficiency, this is desirable. What is the stability of the catalyst, how much water we can treat per unit amount of catalyst, what is the reusability once the activity goes down. So, can we reuse it after maybe some treatment of the catalyst, so that its activity is generated back, and what is the price in large scale treatment. So, it will depend upon all these parameters. So, catalytic wet power oxidation technique is also being studied a lot in literature. It is being used mostly for degradation of those organic compounds which cannot be treated otherwise by simple techniques. So, this is where they are being used. So, like for pyridine, quinoline, many studies are being done for difficult to degrade compounds, or which are called as recalcitrant compounds. So, they are being targeted to be treated by this technique. So, with this today we will end this lecture. We will continue with further AOP methods in the next lecture. Thank you.